We now know that the ID VDS characteristics of a MOS transistor or the port 2 characteristics of a MOS transistor are not exactly flat in the saturation region. Okay. So, they have a slight upward slope. The current does increase slightly with increasing VDS. Okay. In terms of the expression for the current, we have this additional factor 1 plus lambda VDS. What we need to do now is to find out the effect of this on the small signal model. Okay. So, the small signal model, so far as we know, consists of just the GM. Okay. So, this is the gate, this is the drain, and this is the source, this is VGS, and this is GM VGS. Okay. And this is the incremental VDS. This, by the way, is the small signal incremental model, and the symbol for the MOS transistor itself is like that. Okay. Now, this GM is nothing but the partial derivative of ID with respect to VGS, and if I calculate that, I get mu n Cox W by L VGS minus VT times 1 plus lambda VDS. So, this 1 plus lambda VDS appears in this expression as well. Okay. More importantly, earlier the conductance that we call Y22, that is the conductance that appears across the terminals of port 2, in case of a MOS transistor, we know that it is called GDS, the drain to source conductance. The partial derivative of ID with respect to VDS, this we had thought was 0. That is, basically that is the slope of this curve, the slope of the red curve here is 0, but we now know that it is really the purple curve. So, the slope is not 0. Okay. So, this is not really the case, and if we calculate that from this expression, you will easily see that it is equal to lambda times mu n Cox by 2 W by L VGS minus VT squared. Okay. In fact, the biggest qualitative change appears in this GDS. This GDS was originally 0, there was no conductance here. Now, we have a conductance GDS given by this expression. Okay. The value of GM is also modified by some number. Earlier we were calculating this, now we have this additional modifier, but this is not a big change. As I said, this lambda VDS is expected to be small compared to 1. Okay. So, the value of GM changes a little bit, but we do not usually worry about that. Okay. Whereas, this one it was 0 and now we have a non-zero conductance. Okay. So, this is the most important effect. So, we have a non-zero drain to source conductance, and of course, this applies to the incremental picture. We have a non-zero drain to source incremental conductance. Okay. So, what do we do in practice? The expression for the current in saturation is mu n Cox by 2 W by L VGS minus VT squared times 1 plus lambda VDS. The expression for GM is mu n Cox W by L VGS minus VT times 1 plus lambda VDS, and the expression for GDS is lambda times mu n Cox by 2 W by L VGS minus VT squared. Okay. So, everything changes, and these things are now a little more cumbersome, because you have a nonlinear function and you also have this additional variable. So, usually what is done is, for operating point calculations, this is ignored. Okay. So, we just do not even worry about it. When we want to find the drain current, we base it only on the gate to source voltage. Okay. This is inaccurate, But again, like I said earlier, the goal is to understand the phenomena, not to make the calculation to the last decimal point, because even if you include this, this itself is not accurate. The actual model of the MOSFET is really complicated. Okay. So, to get some insight into the operation, this is good enough. Okay. So, for operating point calculation, most often we just use this, and if we do have to use that one, we actually use incremental calculations to find the effect of this one. We calculate the approximate operating point only using this part of the expression, and any effect of this we add in later. Okay. So, that is what we normally do, and similarly for GM also this is ignored, okay, because again we will operate under the assumption that this lambda VDS is much smaller than 1. So, we will ignore this and calculate GM based on only this one. Okay. And of course, for GDS we can't ignore this lambda. If we do, we will get 0 and we will be ignoring a qualitatively significant phenomenon. Okay. So, for GDS we use this. Now, you notice that this part of the expression is nothing but ID. Okay. So, we say that GDS is approximately lambda times ID. So, the GDS itself is proportional to the drain current, and this is the expression that is most often used. We calculate GDS using this expression lambda times ID. So, I hope this part is clear. Again, this is the expression, but for simplifying the calculations, we ignore this 1 plus lambda VDS term while calculating the operating point current or while calculating the GM of the transistor. Okay. But we do take into account lambda while calculating GDS, because that is what gives you a non-zero value of lambda. Okay. And just to get a feel for the numbers, let me assume that lambda is 0.05 inverse volts. Okay. Now, let me first assume that lambda equal to 0 and calculate everything, and I will use the same transistor as I have always been using, with a threshold voltage of 1 volt and a current factor of 100 microampere per volt square, and I will use an operating point VGS to be 3 volts. If I do this, I know that if I assume lambda equal to 0, I get a drain current of 200 microamperes. You can verify this very easily, and I also get a GM of 200 micro Siemens. Okay. And the drain source conductance will be 0. By the way, let me also assume VDS equal to 3 volt, so that it remains in saturation region. Okay. So, this implies saturation because VDS is more than VGS minus VT. Okay. Now, if I take this lambda value 0.05 volt inverse, what do I get? I get ID to be whatever I got from the original expression times 1 plus lambda VDS, and lambda VDS in this case is 0.05 volt inverse times 3. So, this is 0.15. Okay. So, the actual value of ID turns out to be 230 microamperes. Okay. So, there is an error if we assume 200 microamperes, but that is okay, because if we include this in every expression, we will not be able to calculate anything at all. Similarly, GM will be the GM calculated from the original expression, which is 200 micro Siemens times 1 plus lambda VDS. These calculations are quite simple. So, that is why I am not going through them step by step. So, I assume that you can work out these things quite easily by yourselves. Again, this will turn out to be 200 micro Siemens times this number is 0.15. So, this will be 230 micro Siemens. There is an increase in GM if you use the complete expression, but usually we ignore that. Okay. And finally, GDS itself would be lambda times ID that we originally calculated, which is 200 microamperes. Okay. So, lambda is 0.05. Now, 0.05 times 200 microamperes is 10 micro Siemens. Okay. So, our model will consist of GM VGS, and we will continue to use GM of 200 micro Siemens, okay, ignoring the 1 plus lambda VDS term, but significantly we have a resistor here between these two, or a conductance whose conductance is 10 micro Siemens or whose resistance is 100 kilo ohms. Okay. This is the gate, this is the source, and this is the drain. So, the most important effect of this lambda is to introduce an incremental conductance between the drain and source of the MOS transistor, and this will directly affect the characteristics of the common source amplifier. What that effect is, we will analyze in the following lessons. Okay.